Hi everyone, my name is Sambhav and today I'll be talking about my third assignment, which is basically a game of police and thief to be performed on a graph. And these graphs are generated by NetGameSim, which we have been using since our project one. So NetGameSim is actually producing a original graph and some perturbed graph. Uh, and then we consume those two graphs from the .ngs file. We load them, and that's how we represent them in some intermediate format that is consumable by our server code, and then we play the game. So welcome to this project of mine, and I have named this as Graph-Heist using NetGameSim. This project simulates a game involving a policeman and a thief navigating through a graph, which are produced through NetGameSim, as mentioned earlier. The application is built on using Scala and Akka actors with a focus of demonstrating actor model concepts and graph algorithms. Right, so it's designed to demonstrate the power of actor model in handling complex interactions with a graph-based game environment. The game is played on the perturbed graph, and the players can either a thief or the police navigate through the graph, which and the moves are determined by the confidence score. And this is again we are determining based on the similarity scores of the nodes and edges from the perturbed to the original graph. That's how we are actually deciding what moves can be made for a particular player. So, and with the help of the similarity scores, we are calculating the confidence scores. So if suppose there is a node 3 and it's the successes are 4, 5, 6, so we'll calculate the confidence scores of 4, 5, 6 from the perturb to the 4, 5, 6 of this node in the original. And if suppose the confidence scores come out to be I mean the fourth node has the highest confidence score, so we'll move to that score because there's a probability that there's no new there's that node is particularly not removed and will not get stuck, and that's not an illegal move. So that's how we are actually deciding the move. So this strategy is basically based on the confidence score. So there are some game rules as well. Initially we are placing both of the players at some random position. We have also uh, made a function which places one of them on a random node, and the other one is placed at some other node which is a bit further from the place at which the opponent is placed. So in order to avoid that, they don't land on the same node again and again, so that the game can be actually visualized more easily. And players move alternatively. And so this game of thief and police, what I interpreted as in a real life thief and police. So the win conditions for thief is different to what the winning conditions of police are. So in this graph, there are some valuable nodes, and the thief's target is to hunt those valuable nodes. And if suppose thief lands on a node which is valuable, then he wins and the game is over, and the game is to be restarted again. And if suppose police is landing on a valuable node, then it means nothing for me. And that is how I implemented it. So police only wins when the thief gets stuck. And by stuck, I mean they get stuck at a node from where they cannot move to any other node in the graph. And so all the valuable nodes are actually saved in the graph. And that's how the police wins. And even police can get stuck on any such node, and in that case thief automatically wins and the game is over again, and they can play a new game and they have to restart a new game. That's how my implementation and my interpretations are for this game. The features we have is it's a graph based game simulation. Second, it's an actor model implementation using Akka, which is very effective here because of the fact that we do not want the server to stop, and it essentially helps us to achieve asynchronous execution. And we have RESTful APIs for the interactions here. So while the server is up and we are exposing the endpoint to the players, they can hit their endpoints and play the game. So there are four crucial endpoints in this game. One is like for moving the thief. Second is for moving the police. Third is for getting the state, which helps us to know what exactly is the state right now. And third is reset the game, so that whenever the game is over, there is one endpoint to reset the game and start a new game again. All these are the getter endpoints, because according to me, since we are not creating any resource on the server, we are not posting anything on the server. So it makes sense that we have these endpoints as getter endpoints rather than post endpoints. So also because of the fact we do not have any database here, we are not storing any information. Hence, these are something like we are playing around with an algorithm. We are fetching some data from the server itself. So that's the thing, that we are not creating anything on the server. So all of these endpoints are the getter endpoints. And so yeah, we have different modules. I have implemented it in a layered architecture. We have different packages here, so that there is not tight coupling at all. The application is quite loosely coupled. And so there are the different modules. Like one module is like the actor module, which will have our actor itself. One is like the API module, which will have the server, which will host all the endpoints. Then we have the service model, which will have the game logic. Then we have the game state class, which is actually representative of the state of the game, which holds the information like game is over or not, which holds the last player, the result of the game right now, the thief position, and the police position. So these are the major modules we have. And then there is another for the automated client as well. There is one more package for client, automated client, where the logic for automated client is in there. Let's move on to the steps and workflow. This will help us to understand, and it will actually lay the foundation of understanding the game, how exactly the game is being built, what is the design of the game. So we have the server here. So initially what we do is we initialize the actor system, and we load the graphs, the perturbed and the original graphs that have been provided to us through NetGraphSim. So like every time, essentially what we do is we parse the NGS file, we load the graph, and here we are representing the graph with the help of Google's Guava library. And we are loading the graph, we are representing with the help of Google's Guava library, and then we'll make move on them. So we after loading the graph, we are instantiating the actor object, and with the help of these loaded graphs. And then we create, so the game actor is created. Then we create our HTTP server, and we bind the routes that we have defined. We'll see in the web server game file itself. So let's go to that file right now. So this is what I'm talking about. So our entry point is the main function, which is calling the start method of web server game dot start. And when we traverse to that function, this is the function where we are having the actor system. We are loading the graph, the original and the perturbed graph. Then we are instantiating the actor with the loaded graph. We are passing the perturbed graph and the loaded graph here. And then we are creating our HTTP server. We are binding our routes here, and we are bringing the server up. So this is the story tale here. When the server is up and running, and it listens to the HTTP request. And what happens afterwards is, like, whenever any client makes the request, so this request is being received by the respective route handler. And then what happens is, since we are working with Akka HTTP module here, so the HTTP handler routes basically use the Akka pattern to send message to Akka actor. And this is one of the major advantage of this framework that we are using, is that it helps us to achieve asynchronous communication. And with this kind of client server architecture, it really makes sense to have such a thing in place. So if suppose there are multiple simultaneous requests coming in, the server doesn't has to wait for one request to be completed, because this is like we are submitting the message to the actor itself with the help of this ask pattern. And so the game actor is the one actor that we have in our project, which receives the message, and it determines the next move with the help of communicating with the game logic, and manipulating the game state that we talked about. We have our separate class for game state. So let's move on to game state as well. This is our game state, which will hold the thief position, police position, game over, result, and last player. This is our game actor class, where sorry, where we have move thief for the movement of thief, for move police for the movement of police, and we're getting the state and the reset game again. So then we have the get next move here again. And so this game actor interacts essentially with game logic. And game logic has the algorithms for placing the players initially at some random nodes far from each other. And then we have this function of calculation of confidence score, which is called through calculate next move itself. Uh, these are the crucial functions which are working in behind to determine the position for the next move itself. So we can clearly see that the calculate next move is being called from game actor.scala at position 8 and 65. So this is a game actor.scala is pointing to calculate next move, and calculate next move calls calculation of confidence score. So that is how the flow works. And so when the game actor actually after doing the calculations and confidence score thing determines the next uh, determines the position, it moves to the that particular position, and then it responds back to the client itself. And that is how the execution flow works. So the client send the request to the route handler. The route handler uses the ask pattern, and it basically communicates with the actor itself. Actor does all the calculation behind all the logical thing with the help of game logic and game state, and then it makes the move. And it also checks whether that move is a legal move or not, whether the player is stuck and it cannot move further, or whether the move they made for any player like thief, and the thief is already landed in a node which is a valuable node. So according to that, they send the response to the client itself. So that is why the direction is like that client send the request and it get response from the server, and this is the magnified view of our server, how exactly the things are working. And if suppose there's a request for the automated client thing, we have exposed an endpoint for invoking this code as well, where this automated client plays the game automatically, and it only stops when it encounters any terminating conditions, like the game is over because of the players are stuck, or if the thief has landed on a valuable node, or if the police catches the thief. So these are the conditions which are actually the terminating condition, and the game is over. And for the automated client right now, I have kept like the whenever this automated client code is invoked, it will actually play 5 games. It is configurable, we can change. And so right now, just to observe how exactly the game is being played, since it's a random thing, because when the initially the players are placed at any node, they are placed randomly, so the results will be different. So that's why, just to observe it more clearly and to understand it betterly, I have had this 5 games in my mind. And so the report is being produced for the automated client thing only, so that we can visualize what all nodes the players move to, and what games did this thing happen. So this is a major workflow we have, and this is our project structure. As we have actors package, we have API package. Actor will have this game actor.scala. We have web server game.scala. Then models consist of game state, and the game logic is in services, and utils obviously for loading the graph, and the net graph and the graph loader.scala. And correspondingly, we have the similar structure for test. And so this is how our project structure is like. So what we can do right now is we can invoke a project. We can invoke this main method, and I have already things in place in my configurations, run configurations. So I'll just execute a project so that the server will be up, and then we'll start hitting the endpoint. So our server is up. Let's go to Postman. Let's see what the state is right now. So since none of the player have made the move, so it's like there is no position that is assigned to them. So let's start with the thief. If suppose thief makes a move, so thief is at position 10. So right now I'm playing on a graph which is having nodes like 20 or 21, and let's see and visualize how exactly things are happening here. So this is my graph with 20 nodes or 21 nodes, since we have 0 here and the last node is 20. So we have 21 nodes here. And yeah, we are moving on the perturbed node, and the confidence score is being calculated with the help of the original graph. So thief is at position 10. Now let's make a move for police and let's see what happens. So police is placed at position 19. So thief is here and police is here. Now let's check what is the state is right now. Initially it was unknown since the players didn't made any move, and now it will show that the thief is at position 10 and police is at position 19. Now let's make a move for thief again. So thief moves to position 6, and now let's make a move for police and police makes a move to position 20. So we can see that we are approaching to a node which is a leaf node for police, and they might be stuck after 16 and probably the game will be over. So let's see what happens. So we made the move for the police, which is 20. Now we will make the move for the thief. So thief moved to 17. And now we make the move. So yeah, here the thing is we can see that clearly there are not much options to move here. So whatever is coming, they are moving right now. But yeah, the confidence score is still being calculated. So we have the loggers here. We can clearly see the calculation of confidence score and the node objects that are being used for calculating the scores here. So now thief is at position 17. Let's make the move for police. So police is at position 16 now. Now let's make the move for thief. Thief makes a move and he has position 5. Now it's a turn of police itself. Just notice that now after 16 there is no way to go anywhere in the graph. So now police should be stuck here. So yeah, police is stuck at node 16 and cannot make a move. Game over, restart the game. Now even if thief tries to play, let's see what it gets. So yeah, since police is stuck, now thief has won automatically because police cannot make a move in the graph and thief is free to move at any node in the graph. So they actually won. So even now if police tries to hit the endpoint, they won't be able to, and they'll get the final concluded message that thief has already won and the game is over. Now, now let's see the state here. So police had stuck at 16. This is actually represents the original state, what exactly happened. So we'll have to reset the game again and we'll have to play again. So we reset the game, we'll check the state again. What's the state? And the state is like there is no position assigned to any of the thief or police. Now let's start with police here. So police is assigned a position 10. So police is probably here. If we make the thief move, thief is at 16 now. Thief is already placed at a leaf node. Now police makes a move. Sorry. Police is at 6. And if thief makes a move, thief is stuck now. So thief is stuck at node 16 and cannot make a move and game is over, restart the game. So now if police tries to hit so police won as the opponent got stuck. And that is what we discussed. So I've tried to make the message more customized so that it appears for the opponent and it is like consumable and they understand what exactly is the state of the game. Although if there is an endpoint for get state, it will reflect the original what exactly was the reason for the game to be over. So we reset the game again here, and now we'll hit the automated client and we'll check the logs as well, and we'll see the report being generated. So let's hit it. So the automated play has started. Let's go to the logs. The game is still going on right now. We can see here. It's game number 4, which is being played. And now the game number 5 has started and finished playing 5 games. Maybe we can play once more. We have invoked it. Yeah, and we can see the report.txt now. So the last game 5 was congratulations. Thief has found valuable node at 8. So let's verify it. So police might have started the game and they got placed at node 18 and it was here. and then the thief actually was placed at node 8, and that's how they won the game itself. So this is the second invocation. We can see the results of it, and we can see in the log that thief is stuck at node 16 and cannot make a move, and that's what is printed here in our report.txt. And this was game number 5. That is what it should be here. Yeah. Okay, so this is our report here, and I have already made the EC2 instance here, and we can invoke the instance. Let me refresh it. So the instance is stopped right now. And by the way, in the report, I have mentioned what the strategy is being used. It's confidence score as required in the GitHub description and game number 5. And yeah, let's verify this as well, like how are the moves were. So I'll just go to our graph. So thief is at node number 4. So thief is at 4 and the police is at node number 12. So 12 is here. So probably police make the move first and thief was placed here. And then because yeah, whenever any player starts the game, then if suppose police starts it, then we would not be looking for the position which is before the 12. We are considering the directional edges here. So that's why I'm assuming the police started the move first and the thief was placed here. And then after that, police made a move at 7 and thief made a move at after 4 to 10. Then police made a move at 15 and thief made a move from 10 to 6. And again, police made a move at 3 and thief made a move at 17. Then police made a move at 4. So after 3 to 4, that's correct. And thief made a move from 17 to 5. That's correct again. Then police made a move to 10 after 4 to 10. That's correct. And thief made a move from 5 to 13. Right. And then police made a move from 10 to 6. Then thief made a move from 13 to 19. Then police moved from 6 to 17 and thief made a move from 19 to 20. Then police moved from 17 to 5 and thief moved from 20 to 16. Now after 16, this is the critical point because when they make a move again, they'll be stuck. So police makes a move from 5 to 13 and now thief again makes a move, but this time they are stuck because they are at 16 again. They cannot go to some other node from here. So that's why the result is thief is stuck at node 16 and cannot make a move and game is over. We can see the game number 4 here. So thief actually started the game and he just got randomly assigned to node number 9 and that was a valuable node. So what happened was that the thief already went on to a valuable node and they won. So there was not a chance that police would make a move. So that's why the result of this game is congratulations, thief has found a node at valuable data at node 9. Game over, restart to play again. So we can also check for this in the logs itself in order to verify. Yeah. So yeah, this happened, actually happened this. So that's why we got this message. Then game number 3, where what happened? This is also an interesting case where that we should discuss right now. So first we should look for the log here again. Yeah. So this is the thing that thief is caught by the police. So if thief is at 8 and police also got placed at 8, so in our graph, thief was at 8. So when thief is placed at 8 and the algorithm starts for looking on the positions after 8 for any further position from 8, there is no position. That's why the police also got placed at this node. And although it is a valuable node, but since the thief and police are at the same node, so the thief is caught by the police and the game is over. So that's why it shows the message like that. And similarly for Game number 2, thief is at 20 and police is at 7. So police is at 7, thief is at 20. Then police makes a move to 15, thief makes a move to 16. Then police makes a move to 3 and thief makes a move to 16 again, and they are stuck. And that's how it ended. And this is again the case where the thief is caught by the police. Sorry. So this is our report. And then let's execute this on a EC2 instance. I've already created the instance here, already tried and tested it. So I already have it. So what I'll do is I'll just start the instance. It'll take some few minutes, like maybe 2 to 3 minutes probably. We can wait till then. We can discuss this case again here in this game. Actually, police is stuck here. So the game result is, so thief started at node 17. Thief was here. Police was at node 20. Then thief moved to 5 and police moved to 16. Then thief moved to 13 here, and then police got stuck. So the game is over. So that's how the games are played here. Uh, yeah, and also I have already placed my jar in the on the S3 in the S3 bucket. So I have this police thief game bucket here, which has these three directories: inputs, jars, and inputs. I have the same graph which I used for demonstrating right now in my local, the .ngs file and the .pertot file, and then I have the jar file for that already in there. And this is the output directory. I already tested it, so yeah. Uh, let's check if our instance is already up or not. It's initializing. Yeah, meanwhile, we can do is we can execute our test cases. So I have covered approximately 17 test cases here. So we'll do SBD test and then we'll see the results of all the test suits that we have in place. Yeah, so all the test cases are succeeded. So the test suits we had was game actor test, and then web server game test, and all these test cases. Then before that we have game logic test, then we have game state test. So these are all the test cases we have. Our test cases we are done with, and now let's check our instance. Yeah, our instance is up. uh, let's try to connect with it through SSH. So we'll SSH to our instance. Okay, here we are. So I'll go to my app directory, and I already have, okay, I already have this police thief game.jar. And what I'll do is I'll just invoke this jar. So I have this command java-jar. I've already mentioned this command even in my readme I've mentioned for in case if we are running this jar on EC2 instance. So I have the arguments here. I'm giving the path of my S3 bucket where actually we have this .ngs for original and for perturbed. And yeah, I'm also creating report.txt here also, since we have already been doing the report creation and the results creation in S3 bucket. So our server is up, and I'll have to get the public IP of my instance. So that's my public IP. I'll just use this instead of localhost. Okay, so let's try hitting get state. So yeah, we are able to hit it. And so the state is right now, none of the player have made the move. So let's try to make a move for thief. So thief is at play a position 10 again. And now we can make the move for police. Police is at position 5. Okay. And then we'll make a move for thief again. Then thief is at position 6. So we can see the calculation of confidence score here. Then logs are getting printed here, the perturbed node object and original node object for which the confidence score got calculated. Then we have uh, police move here, then again thief, then again police, then again thief, then again police, then again thief, then again police, then again thief. Police is at 16, and we saw that 16 is the leaf node, so probably police is going to get stuck, and they got stuck. And if the thief tries to, and the thief one as opponent is stuck, and if we try to get the state, so yeah, police is stuck at node 16. That's the original state, and we are getting all the logs here in the system in our instance, right? So now let's try with the automated client thing, and we'll see the results, what exactly happens. So we'll invoke this, and now let's see the logs here. The game is being played, the log is being printed, they are starting with the game number 4. And yeah, so they are finished playing 5 games. Now let's check our result.txt. So we can see the report.txt, sorry, it got created and the timestamp is 11.5. We can verify with our instance timestamp. So it's 11.5. So it just got created. So the earlier one was overwritten, right? So the earlier one got removed and we got the new report.txt, and we can check our report.txt and we will be able to see the games played here. So thief caught by police at node 19, and yeah, and game number 4 has like 19, 26, 17, 15, 30. Yeah, thief is stuck at 16. So that's what the scenario is. And yeah, the last game was thief was caught at node 19. Yeah, it is correct. So our uh, jar is working here, and the service is reachable from our postman itself. And yeah, these are the some of the outputs that I've posted here in order to understand what kind of responses that the game gives us and how exactly our report.txt look, what all things we are giving as per the requirement that we wanted to see, the strategy that we are being used, what the game is, and what the thief moves are, what the police moves are, and the result and the reset thing. And this is a sample graph that we had been working on while playing the game to understand. And yeah, the technologies used, we are using Scala and Akka HTTP, which is the like the heart of the project here right now, and the actors, and the Google Guava obviously for representing our graph here. Thank you so much. That's all from my side. Thanks a lot.